Welcome to the Parallel Programming Concepts course. This is week 4 and we're going to talk about accelerators. First of all, I want to try to motivate you for the topic. In the last week, we were discussing shared memory systems and we learned a lot about the ways to program those systems, and we were even looking into Pegasus languages to deal with non-unified memory architectures. And the question of the last week was, so those languages help programmers to achieve the speedup, but what could be achieved if we had specialized hardware in the first place that brings good performance for parallelization? So let's start with this question. What is specialized hardware anyway? And every one of us actually has a lot of specialized hardware in his computer, apart from the central processing unit that is there for general purpose tasks. We have some special hardware for special tasks, like for example the GPU, who is doing all the graphics intensive processing. And I mean, the CPU could do this as well, but the GPU is usually way better in doing this and way faster. So GPUs would be one graphics cards would be one kind of this. GPUs is actually the processor of the graphics card, and I'm using both terms in this lecture. Another specialized hardware would be sound cards. In the past, sound cards were very big and it was a very compute intense task. Today, processing of sound is fairly simple as compared to processing of those 3D graphics as we see in the background. Another thing would be physics cards that were discussed some years ago, where people tried to build cards that were pretty good at doing all physical simulations. Today we can achieve this with GPUs as well, or CPUs, and we are going to see how this works. We could also think about other applications, that could benefit from special hardware. For example, encryption would be one, compression would be another one. So we could have special hardware that is very good at encryption or compression, and that speeds up those tasks. Or codec parsing. This is very popular for all those movies that, like if you have a very small device and you want to see HD movies, then it's pretty good if you have special hardware that's pretty fast with decoding those movies. Then you could think about standard protocols that are used all the time, and on small devices like phones or so, it would be great to have special hardware that deals with this. You could also think about text matching, regular expressing matching. All those tasks occur again and again, and it would be beneficial if we had special hardware. And actually, accelerators are everywhere, even today. And I wanted to start with GPUs, as I told you. Today we have special GPUs who are used only for computations. And on the picture we see an NVIDIA Tesla card, and if you look very closely you can see that this card doesn't even have GPU ports anymore. So you cannot plug a monitor into this. This is solely for computation. Another thing is that in each of the modern Intel CPUs, and the heart of each of those chips, there's the GPU inside as well. So those special tasks like accelerating those picture generations are already in those CPUs and in those cards. AMD has something very similar. They call it APU, for Accelerator Processing Unit, and they also have a card, a graphics chip inside the CPU. And then we also have the Intel MIC, which is a new card from Intel that tries to build something that is as fast as a GPU with standard CPUs. So you have an accelerator board that you can basically plug into your computer and then have all the compute-intense calculations on this board. And this is currently kind of computing with the NVIDIA Tesla technology. And in addition to this, in the background we have two pictures of the best or fastest supercomputers in the world today. Milky Way 2 is the best supercomputer currently, and it is built out of Intel CPUs and those Intel MIC accelerator cards. So those large computers already have those. And the second one is Titan. Titan has also CPUs and a lot of NVIDIA GPUs in it. And as you can see, with those Intel CPUs and GPUs, basically all the desktop computers already have accelerators, but we also see them in server computers, where NVIDIA Tesla is a special case, which is basically used for server computers only. We have high-performance computing, as we've seen, and we also have embedded computing, where we have a long tradition of having special processors for special tasks in those embedded devices. And a subfield, so to say, of special devices or embedded hardware is phones. So even in phones, we have various accelerators for the tasks. Okay. We also have a wide variety of applications that can be executed on those accelerators. And the first of all would be simulations. This is a standard example of CUDA, of NVIDIA's GPU programming framework. And here you can see that you can have a simulation of, basically this is a surface of water, and you have like some green stuff on it, and you can move your finger around it, and then it simulates how those particles on the surface of the water would behave. And this looks really realistic. So this is a physics simulation running solely on the GPU. Then we have a more complicated physics simulation maybe, or a more compute-intense one. This is an n-body problem where you have a three-dimensional space, and in the space you have a number of particles, and they have gravity or forces that they apply on each other, and then the whole thing is moving according to those forces. So each of the particles is interacting with all the other particles in that space. And if you add more and more particles, then this becomes more and more complicated. And actually, it's only an approximation, because in real physics, it's pretty, I think it's even impossible to do the actual calculations. But with such systems, you can have a very good simulation of what will actually happen. And since those two look still pretty much like graphics because they visualize the results, I have one other example, and that would be a radix sort, where you could use, here again, an NVIDIA GPU to do a very fast sorting of a very large number of keys and values. And you could think about database applications or something where you could run something like this. And those examples are all the basic examples that come with the programming frameworks of modern GPUs. Okay, and since they are pretty much easy to program for and use for those kinds of simulations, there's a variety of application domains that already use those cards. And on NVIDIA's GPU application domain page, for example, you can see all those domains and have examples from those domains and what they did. And as you can see, a lot of simulation and physics or chemistry or bioinformatics, but there's also data science and computational finance, for example. So there's a wide variety of fields that actually already apply GPUs to get good performance. So we could ask ourselves, what's in it for me? So what do we gain from using accelerators? And what we can gain is a very good performance. So this is one example that we actually build ourselves. It's a Sudoku validator. So you have a very large Sudoku field. For example, 50,000 means 50,000 times 50,000 fields. And you get such a big Sudoku field, and then you'll just look at if it's correct or if it's not correct. Okay, and in this benchmark, we see that the CPU needs a very long execution time. So on the y-axis, we have the execution time, and lower is better because lower is faster. And we see that the CPU takes a long time, while the two GPUs are pretty fast. So the short-term view for using a GPU is that you can get good performance. And currently, we are at the Kepler architecture, and the Kepler architecture gets very a good gigaflops per watt ratio. That means for less energy, you get a lot of gigaflops out of it. And in 2014, this year, we will see Maxwell. And Maxwell we'll even have 15 gigaflops. So what is gigaflops actually? Gigaflops means 15 gigaflops, for example, would be 15 and then 9 zeros floating point operations per second. And what we see in the background here is the development of the supercomputers in the world. And what you can see, first of all, and this is why I like this picture so much, is that our computers would have been in the top 500 supercomputers in the year like 2004, for example. So 10 years ago, our standard computers would have made it into the top 500 supercomputers. That's pretty awesome. And another thing is that a single Maxwell GPU will have more performance than the fastest supercomputer in 2001. So even though our computers would make it into the supercomputers, they would basically be at the last places, like number 500 or something. But a Maxwell GPU would be number 1 in 2001, a single Maxwell GPU. So this is where we are today. And this is pretty amazing because 10 years ago, the simulation that you could do there on the best computer in the world, or the best, one of the best computers in the world, that could be done now in your computer. So we have a great opportunity for running very realistic simulations, very realistic applications, doing a lot of number crunching in your computers. So in the short-term view, you have a lot of performance. In the middle-term view, you even have more performance because actually those performance output of GPUs are increasing dramatically as compared to CPUs, for example. So this picture shows the hockey stick performance development for GeForce GPUs. Both are GPUs from NVIDIA again. And on the bottom you see all the developments for the CPUs currently. And another thing that we also have is that the memory bandwidth gets also faster and faster. We've seen that the memory wall is a big issue, and with GPUs you can, in the same time frame, get more memory to the GPU, so the bandwidth is better, and this way you have the impact of the memory wall is not so big on GPUs. Okay, so this is the middle-term view, and in the long-term view, there's no way to get around this really, because accelerators are everywhere today, but they will become increasingly important because they are a way to get around those walls. So we've seen all those walls, and the GPUs and the accelerators, they have a special field that they are pretty good in, like those pixel rendering tasks. And since they are specialized for one single field, you can get orders of magnitude of better performance. And this way, you can build them in a way that they bypass some of the walls. We will see this in a minute. And also, they are currently already everywhere, and they are increasingly important for all those fields. The best 2 supercomputers in the world are currently using accelerators. And there's a variety of algorithms that could be sped up with accelerators that are used basically in all modern software systems, like XML parsing, encryption, decryption, regular expression matching, or that are even in your operating system, like again, encryption and decryption, but also compression. So all those fields are already and will be increasingly accelerated in the future using those technologies. And now to the question, why do they get so fast? I mentioned the walls before. We've seen them in the last lecture. So we have all those different walls, especially memory wall and power wall are crucial here. And accelerators have a way to go around this. So for CPUs, we need to support all types of software. We need to support all types of programming models. We need to support a large variety of already existing software. We need to make sure that a software from 20 years ago still runs on the CPU of tomorrow, and also the old operating systems, for example. And this makes it hard to do something against the walls because there are so many rules that you have to stick with in order to make sure that all the old software still runs there, and that all those other software and programming models that are out on the market will be supported on your next CPU architecture. The story is different with accelerators because accelerators only need to support a very limited software of software and programming models, because actually they were focused so much in the past that everything was built on hardware and there wasn't even real software there. And now that they open towards software and towards programmability, you can program them, but they still only support a very small subset that's very good for the accelerator because they are so special purpose and they don't even aim to be general purpose at all. And also, legacy software is usually even more strict than the actual generation, so they add programmability features, and all the old tasks will still run because it was stricter in the past, so to say. And they were also more limited. So the new generation will bring more performance to the old tasks, and still can add programmability features because there were so less of them in the past. And so the impact of the walls is really not that big. Because all the memory guarantees that you have CPUs, like if you change one part of the memory, then all the other cores would know. This is not true for GPUs actually, and so the memory wall is not that big of a problem because you don't need to inform everybody. And also, they have a very special mechanism. You could think of this as an ILP mechanism that we will talk about later in this lecture, that allows them to hide the memory latency, to hide the slow memory by having more threads that run while others are waiting. And since they are so focused on what they are doing, also the power wall at the moment, at least, is not that of a big problem. Okay, so they bring a strong parallelization because they have so many small threads and better speedups, and we will see how this actually works. But first, this is basically the development of the last years or last decades. We had CPUs getting more cores, and currently we are at multi-core, and we have some first CPUs that are able to do this many-core thing where they have like multi-cores 4 or 8 or 16 cores. Many-core starts with 50 or even more. And GPUs usually have around like hundreds of cores, where CPUs have today 16 max. And the Intel MIC is the first accelerator that we've seen before that is more like a CPU but has a number of cores, and it has 60 cores, around 60 cores currently, which is way more than old CPUs had, because they have to cope with those walls and get more and more parallelization in order to deal with this. On the other hand, we had accelerators, and accelerators developed towards general purpose computing. So they had a fixed function in the past where you could basically just do the very tasks they were designed for, and then they become partially programmable because people thought, oh well, it would be great if we had some way to tweak the parameters a bit, or to change the way that the colors are chosen or something looks using the GPU. Those are called shaders, or were called shaders. And now they are fully programmable, so this is what they are aiming for. You can write standard C++ programs and run them on the NVIDIA GPUs, or on the AMD GPUs, or basically on all the modern GPUs supporting OpenCL. And we will see how this is done later, but they are really way more programmable than in the past. And since they are so close now, because GPUs are so programmable and have many cores like for years, and since Intel CPUs were programmable all the time and they now have so many cores, those vendors, Intel and NVIDIA for example, are actually competing today on the market in order to get the shares for those future things, those future markets. Okay, so one last thing here is that on the left-hand side we see what CPUs are actually built for. So each CPU can run a thread or tasks that are very different, and they can work on the same data or on different data, and then they produce some results, and the results are aggregated in the end. So this is the fundamental idea. You have tasks that are working together, but tasks can basically do whatever they want. So there's no strict rules on the tasks. With accelerators, on the other hand, you have all, especially for GPUs, all the tasks are doing the same. And also with other accelerators, you have usually the situation that since they are built for one special purpose, they do this purpose in a lot of parallel, on a lot of parallel data, but they all do the same. So the fundamental difference here is that while the CPU is, can have multiple different work packages running at the same time, GPUs are really focused on doing one particular thing very, very parallel. So the left part would be CPU-style task parallelism, and the right time would be GPU-style data parallelism. And the right part is true for a number of accelerators. Have we seen systems like this before? Indeed, we have. We were talking about Flint's taxonomy before, and in Flint's taxonomy we have one instruction that is executed on a number of data items, and this is actually what current accelerators look like today. So they really have single instruction, multiple data hardware that allows them to run multiple, to run one instruction on multiple data and have this the way of doing the parallelization. Okay, and the next part, we are going to look a little bit more into the hardware, and we're going to look a little bit more into how that actually works and how they get this performance.